How's it going? Today, we're going to be looking at the first lesson for the new unit we'll be covering about probability and statistics for Algebra 2. In previous years, statistics and probability was not taught in Algebra 2, but it has been deemed by myself and some colleagues of mine that it is very important to cover. And so here we are covering it. This starts out simple enough and it gets more and more complicated, and it all builds on this starting material. So, if you are having trouble, you need to make sure you're asking for help and getting help, because you cannot just continue on and not know what's going on, because you're going to get more and more lost. So, you need to make sure it is a responsibility of yours to stay caught up. Ask for help. It will be provided if you ask. So, we're going to start with the fundamental counting principle, the basic premise of what we base statistics off of. And so, the fundamental counting principle is the number of ways in which a series of successive things can occur. Well, let me rephrase that. The number of ways in which a successive or a series of successive things can occur is found by multiplying the number of ways in which each thing can occur. All right, key words at the end here. Grammar aside. It's about multiplying the number of ways in which each thing can occur. So, here is the written out example here. If decision M can be made M ways and decision N can be made N ways, the two decisions can be made in M times N ways. You deal with stuff like this all the time, and you just don't know how many total choices there are. Every day you put on an outfit, right? You're dealing with this exact situation. The number of different outfits you have in your closet will be will be able to be figured out by doing this, assuming everything can match each other, which it can't, but you know. The ice cream shop offers a choice of 3 cone sizes, right? So that's the first thing we're looking for. 3 cone sizes. Let me do some highlighting here. 3 cone sizes, 15 flavors, and 8 toppings. How many cones are possible if you can only choose 1 flavor and 1 topping? Well, the fundamental counting principle says that it's a multiplication of the different ways that each of the things can be done. So if you have to have a cone, there are 3 cones. Then there are 15 flavors and 8 toppings. And so you multiply 3 times 15 times 8. And you get 360 different types, like different possibilities. And that's that. Next up, Virginia license plates consist of 3 letters followed by 4 digits. How many different license plates are possible? Now, a very common mistake students make is that they'll see the numbers 3 and 4, and they'll multiply 3 times 4, and they'll say that there's only 12 different license plates in Virginia. That every 13 cars you'll see a duplicate license plate. Guaranteed. But clearly that is not true if you think about it for 5 seconds. So we've got something is wrong here. What you need to understand is how the decisions are made, right? If decision M can be made M ways. For a license plate, there are 7 decisions to be made. There are the first 3 decisions for the letters, and then the next 4 decisions for the digits. So there are actually 7 decisions to be made. So for the first decision, how many ways can it be made, right? How many different choices do you have for this decision? If it is a letter, right, how many different letters can you use in the alphabet? Now, it was my understanding that you can't use some letters, but we're going to go ahead and assume that you can use all of them, right? So how many letters are there in the alphabet? No? Do you know? There are 26. So let's say that you can use all of them. And so there'd be 26 possible choices for the first one, right? Then for the second decision you have to make, that's for the second slot in the license plate, there's another 26 letters because you can use the same letter multiple times. And then another 26 letters. Then for the next ones, we have digits, which are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So that's 10 digits. 10 digits, 10 digits, 10 digits. They can be reused. So you multiply all of these together, and you get your total number of license plates. And this should look a lot more familiar to us. We have 175760000. That makes a lot more sense, right? Because you were supposed to be able to track people down based on the license plate, so you don't want any duplicates. And so they have got a reserved 175,760,000 possible different license plates. Now, next question. Nick's science test has a section with 12 true or false questions. How many different ways can Nick answer these questions? It's, again, your brain might be thinking 12, and then true or false means 2. And so it's 12 times 2, which is 24. But that, again, is incorrect. That would mean there's only 24 different possible choices, like different tests. If you had 25 students and they all answered it differently, then one of them would have a duplicate, right? And that's definitely not the case. Surely you've been in a class where, it's not like it's random chance and 1 in 12 gets a perfect score, right? Here's how it works. There are 12 questions. And then for each question, you have a decision to be made. And for each of the questions, there are 2 choices, true or false. So 2 choices, true or false among all of them. And so you really have 2 to the 12th power of choices, which is 4,096. And if you're wondering, well, that seems a little bit extreme. How can there possibly be 4,000 different tests? Well, let me tell you. Let me give you a little example here. Person number 1 can put true, 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 true. Person number 2 can put true, 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 false. All right, person number 3 could put true, 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 false, true. And the next person could put true, 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 false, false. Starting to see how we could possibly get 4,096 of these, right? Because we could keep going through all the way up, keep changing them as we go through. Now, next question. To enter their home, the Clayton family enters a 4-digit code. How many codes are possible? Now, we did one very similar to this on number 2. See if you can do this on your own. Pause the video, see if you can get the right answer. All right, hopefully you put 10 times 10 times 10 times 10, because each digit is a choice, and each choice can be made in 10 different ways. 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. And so it would be 10 times 10 times 10 times 10. 10,000. All right, moving on. Factorials. Part of the math needed to do some of this stuff we're going to be talking about is factorials. Factorial, the symbol for it is an exclamation point. And it is the product of all natural numbers from n to 1, which means that if you're taking 9 factorial, it is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. 12 factorial would be 12 times 11 times 10 times 9, right? 12 times 11 times 10, 9 times 8 times 7 times 6 times 5, 4, 3, 2, 1, right? There is a button if you have a TI-84. Actually, I think most calculators have it if you got to find it. But on a TI-84, if you press the math button and then go over to the prob tab at the top, you'll see an exclamation point. that is the factorial. So if you press the 12 first, and then you go into the math, and you put in one of those exclamation points, it'll tell you it is a massive number, 479,001,600. Moving on, 8 factorial. That's going to be 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That is 4,320. Cool. Now, here's something we want to talk about. 17 factorial divided by 11 factorial. You do not want to just put in 17 factorial divide by 11 factorial. Here's what you want to do. This can be simplified quite a bit by hand. You want to expand 17 factorial, or the larger one, down to 17 times 16 times 15 times 14 times 13 times 12 times 11, and you can stop anywhere you want and just put a factorial, but we're going to stop at 11 because the denominator has an 11 factorial. And what you can do is you can actually cancel the 11 factorials. And so you'll end up with just 17 times 16 times 15 times 14 times 13 times 12, which is, of course, 17 times 16 times 15 times 14 times 13 times 12, a massive number. It's 89,10720. See how we canceled those? This can always work so long as you can go down to whichever factorial you want. So if you have like, let me give you a side example. If you had like 6 factorial over, I don't know, 8 factorial, right? You could expand the 8 factorial because 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, right? You could just stop at the 6 and just call that 6 factorial, because 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. So we can stop and just call it 6 factorial. So we could say 6 factorial over 8 times 7 times 6 factorial. Then the 6 factorials can cancel. So you have 1 over 56, not 56. Right, so there's another example like that. Now, here's another issue. 0 factorial is actually 1. There is a reason for this, right? The reason is actually more confusing than you just remembering it, right? Those of you who are curious about 0 factorial being 1, like, ask your teacher about it or ask Google about it, and just for now, just accept that it is what it is. Moving on to permutations. An arrangement or lineup of objects in which order matters. All right, oops, my bad if that was loud. I do apologize. Punched my microphone like an idiot. On accident, obviously. Permutation. Order matters. All right, so let's get into what this is about. Let's look at the first example for a second. How many ways can you arrange the letters in the word dinosaur? Now, arrange the letters. So that means that you'd want to move the D maybe to the end and the R maybe to the front, right? But if you write that out, right, R-I-N-O-S-A-U-D, right? If I switch these two. Is this a different word than this? If the answer is yes, that means that the order that the letters were arranged makes a difference to the outcome, right? A lot of the time, the problem between permutation and combinations, which we'll get into, is your ability to understand whether or not the order matters. And here's what you want to do. You want to imagine that you flipped the order of some of the letters, or in this case letters, and then see, is the outcome different from what you started with? Is this considered a different word than this? And the answer is yes. And because of that, this example follows a permutation, an arrangement where the order matters. Permutations can be worked out like this. N factorial over n minus r factorial, where n is the total number of objects available. In this case, it'd be the total number of letters in the problem. And R is the number of objects to use for the arrangement. So in our dinosaur case, there are 1, 2, 3, 4, 5, 6, 7, 8 letters. So 8. And then it's a permutation because the order matters. And R is the number of objects we're using. So how many letters are we making the new word, right? So we're having to rearrange all the letters. So it's going to be 8 again. Now there's a shortcut, important shortcut, that if you have NPN, it's just n factorial. So that's just 8 factorial. Put that on a calculator and you're going to get 8 factorial, which is 40320. You can also work this out using this formula. Another thing you can consider is that NPR is a function on your calculator. If you press math, and then go over to the probability section, you will see an NPR. Now, if you have older calculators, they'll say NPR. And to use the calculator this way, you have to type in the first number first. So you'd have to type in 8, and then go into the NPR, and then type in 8 after it and hit equals. But modern calculators will actually have a little box where you can just put the stuff in. So sometimes you'll have to do it this way, sometimes you'll have to do it this way. It depends on the calculator you have. But anyway, the answer here is that number of different words. Next up, 7 students are competing in a geography bee. How many different ways can they finish first, second, and third place? Now, here's a situation. Every time on these problems, you want to ask yourself, does the order matter? So say I picked 3 students, student 1, student 2, and student 3, and they were first, second, and third. Let's say, here's my podium. Actually, I need to make sure that there's here's my podium. We've got person 1 here, person 2 here, and person 3 here. Let's say I pick the same 3 people. This is the really important test. I pick the same 3 people, but I try to put them in a different order. So let's say I put 1 here, 2 here, and 3 here. I picked the same people, right? But does the outcome change based on how they were arranged? Well, obviously, because the first place person on the first round got 3rd on this one. That is definitely different. So this is definitely a permutation. So the next thing you have to ask yourself is, how many total things are involved? And things in this case are students. There are 7. It is a permutation. And how many are we choosing out of that? We're picking out 3 people. And so the formula would go 7 factorial over, if you see up here, 7 minus 3, which is 4 factorial. Put that on your calculator. And you're going to get 210. So there are 210 different podiums that can be had. Next up, number 7. Melanie is taking 4 classes this semester: American History, Algebra 2, AP English, and Chemistry. How many different ways can these 4 classes be arranged on her schedule? Now, we're assuming that the schedules make a difference as to, maybe chemistry first and chemistry fourth are considered different schedules, right? And that's because that is indeed the case, right? You have in your class right now, right? Or let's in your junior class, you've got a bunch of students that are in Algebra 2, but they're not in Algebra 2 in your hour, right? They're in it in their hour, which is definitely a different schedule from what you have. So even though you could have the same 6 classes or 7 classes or however many classes you have, if they're in a different order, it's considered a different schedule, right? You don't share the same schedule. You go to the classes at a different time. That means the order does matter. So you have to ask yourself, how many different things are possible and how many different things are being arranged? So there are 4 classes that she's taking. And the 4 classes are American History, Algebra 2, AP English, and Chemistry. How many different ways can these 4 classes be arranged on our schedule? So you have 4 total classes, The order does matter, but you have to pick all 4 of them. And so 1, 2, 3, 4, yeah. And so this would be 4p4, which is going to be 4 factorial, which is what 4 times 3 is 12 times 2 is 24. Next up, there are 16 players on a baseball team. How many ways can the coach make a 9-player batting order? So batting orders definitely matter. Which ones go first, second, third, fourth? Your baseball players can tell you. So this is definitely a permutation. And then the important part is how many total people are involved goes in the front. And then how many we're choosing for a particular batting order goes next. So it's 9. And so you can use your calculator to work this out. 16 factorial over 16 minus 9, which is 7 factorial. I'm just going to go ahead and put this on my calculator for the NPR. It's going to be 16p9. I'm assuming it's a massive number. Yes. 415134720. A massive number. Next up, there are 28 students in Mr. Miller's homeroom. How many ways can the students elect a student council representative and an alternate? That's 2 positions. Obviously, the order matters. If you pick position, for your representative, you pick person 1, and for your alternate, you pick student 2. If you switched them like that, where 2 was the representative and 1 was the alternate, the outcome did change, right? That's the important thing. Try to think, if I pick the same people but in a different order, or assign them different roles, does the outcome change? The answer is yes, then it is a permutation. So you're going to have 28 possible. This is a permutation, and you're choosing 2 at a time. And so you're going to have, this one's easier to do by hand, 28 factorial over 28 minus 2, which is 26 factorial. And so this would be 28 times 27 times 26 factorial over 26 factorial. The factorials cancel. So your answer is just 28 times 27, which is 756. All right. So let's move on. Oh, we got a couple questions left. How many different 10-letter arrangements are possible using the letters in the word automobile? So it's important, using the letters in the word automobile. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 letters, and you're making a 10-letter word. So you've got 10, P, 10. You might be thinking to yourself, well, O is repeated, right? So maybe I shouldn't count it. But it's actually considered a letter in the grouping of the letters, right? So it's going to be considered. How many different 9-letter arrangements are possible using the letters in the word disappear? 1, 2, 3, 4, 5, 6, 7, 8, 9. This is another 9p9. What do you think about this? How many different 10-letter arrangements are possible using the letters? Yeah. So if you have to use those letters, then it would be 10p10 and 9p9. If we were being asked to make smaller words using these letters, like 4-letter words or 5-letter words or 6-letter words, then you wouldn't have 10 here. You'd have whatever number of letters you're looking at. So 10p10 is 10 factorial, which is 3628800, and 9p9 is 9 factorial, and that is going to be 362880. All right, let's move on. Now, combinations are a very similar situation where you're making arrangements, but in this case, the order doesn't matter because either like everyone gets the same thing, or there's no change in the roles, right? Everyone's fitting the same role, and so it doesn't matter what order you choose them in. This is called a combination. The formula is different, right? This is the formula for combinations. And if ever you have an NCN, it's not n factorial, it's just 1. So here's the formula. Probably write that down. Natalie has 16 close friends. How many ways can she choose 5 to be bridesmaids in her wedding? Right? If you need more time to write stuff down, you should probably pause the video and do that. How many ways can she choose 5 to be bridesmaids? Notice that all 5 are bridesmaids. None of them have separate responsibilities. Because of that, this is a combination, not a permutation. It doesn't matter what order she chooses the 5 people in. They're all still bridesmaids. I mean, it might matter to you if you're picked last to be a bridesmaid, but you're still a bridesmaid. So it's a combination, since the order doesn't matter. There are 16 total, and you're picking 5 out. That's going to be 16 factorial over 5 factorial times 16 minus 5, which is 11 factorial. I'm just going to use the calculator feature, though, which is going to be 16 on the front and then 5 at the end, and it gets you 4, 3, 6, 8. But that's how you would write it out if you wanted to. There are 24 students in Kyle's kindergarten class. How many ways can he choose 8 to attend his birthday party, right? It's really important that you keep asking yourself, does order matter here? Well, imagine you are one of the people in Kyle's kindergarten class. If Kyle chose you second to attend his birthday party versus Kyle choosing you 7th to attend his birthday party, does the outcome to you change, right? You should think, no, I still get to go to Kyle's birthday party, whether I was chosen 2nd, 3rd, 5th, 7th, whatever. I still get to go to Kyle's birthday party, which means that order doesn't matter, which means this is a combination. 24 total, choosing 8. You have 24 C8, which is, on my calculator, 24 C8, 7, 3, 5, 4, 7, 1. Last couple of examples for this lesson. Abby is adopting kittens from the pet store. If there are 18 kittens, how many ways can she choose 2? See if you guys can do this. Hopefully you should have thought through that this order does not matter, that whichever kittens she chooses, right? If she chooses kitten 1 and kitten 2, it doesn't matter if she chooses kitten 2 and then kitten 1, the outcome won't change. A key problem students make here is that they imagine, they say, well, no, the outcome does change because she could choose different kittens. But that's not what we're talking about. You need to think if she chooses the same 2 kittens, but in a different order, like a different selection order, does the outcome matter to the kittens or to Abby? The answer is no, because if she chooses the same 2 kittens, it doesn't matter if one was chosen 1st or 2nd. They're both going to go home with her. They're both going to be her new kittens. This is definitely a combination. 18 total, choosing 2. So it's going to be 18C2, which is 153. Next up, 12 employees. How many ways can the manager choose 4 for the Sunday evening shift? Assuming they all have the same job responsibility, that means the order doesn't matter, and it's 12C4, which would be, calculator out, 495. Next up, there are 85 players on the football team. How many ways can the coach choose 3 to represent the team in a coin toss? So order doesn't matter because whether they're all chosen, like if you choose player 1, 2, and 3, or then like 3, 2, and then 1, right? A different order of selection, but they're all still being chosen to go to the coin toss. This is a combination, 85C3. This is going to be a big number. 85C3. 98770. And that wraps us up. Make sure you ask questions over the homework problems, look over the examples, and see what you guys can do.